Okay, so problem set 1 is out. This is due 2 weeks from now in class at 10 a.m. All of these questions are objective type, so you have 40 objective type questions. This problem set will amount towards 5% towards your total grade. And this is due September 12. Objective type questions based primarily on 2 areas. First is atomic structure, electronic configuration, or all those things that we'll be starting from today. And we had like a few things we were doing it in the previous class, maybe a little bit. Then it has periodic properties, very important aspect of understanding the properties of elements. What are the different trends, things like that. So that will be the second part of it. It's there, probably from question 25 or something like that. So each question, all the questions carry equal weightage. Like this, all questions are easy questions, hard questions. All of them are like all equal weightage. If you answer it correctly, you get a +3. If you do not answer it correctly, and you get a -1. And if you don't answer it all, then you get 0 in that. Okay. I did a -1 because someone can just do squiggles and submit it. So that's not, someone can just select all B's and so give it to me. So that's not going to cut it. Okay. So what I also thought that I would split, so I will make problem set 2, which was previously my idea to make it more module 2 based, but I will make problem set 2 also module 1 based, because I think the class can get some more benefit from making it more module 1 heavy. So in that we'll be doing different types of bonding, covalent bonding, what it takes to form a covalent bond, why do we form covalent bond, ionic bond, coordinate bonds, and like basic bonding things, and a little bit more on hybridization and those kinds of like chemistry 2 concepts. So I'll probably see which of these modules can be clubbed in. So your number of problem sets still remain 6. I'll just tweaking around with the actual content of that problem set. Okay. Any special accommodations that if any one of you have to tell it to me immediately, like no later than Thursday this week, so that I can make proper arrangements for your assignments and for your other tests and stuff like that. Panopto, it seems like it's a problem. I will look into it. If I'm not able to solve it, I'm not going to spend too much time trying to solve this. I'll just upload it on YouTube. October 10, I don't know if you can see. I chose this part of the board to write the announcements because then I don't have to move the camera. So previously, when the camera was placed there and I was talking here, I missed most of the things that was happening there. So focus on the class here, and announcements are on that side. October 10, I am traveling to New York during those 2 days. So Professor Saugata Dada, who is the chair of the EPS, he'll be taking the class. But I'm also thinking to reduce the load on him, I can get Ella to be like the guest lecturer in that class. So for half an hour, 45 minutes, whatever she chooses to, she can talk to you about true carbon and carbon sequestration, and you can ask her questions about how to get a job in academia, how to get a job in industry, what they do exactly, do they do experimentation or modeling, and how does an industry-focused geochemistry position function? It's more relevant for many of the graduate students who would be in the job market like really soon, I guess. So it would be good to meet Ella. I will try to be, so she'll be on Zoom, and I'll try to log in via Zoom during that time. Okay, in the last class we did a concept map, which I expect you guys to now think about like how the different fields of geochemistry connect with each other and things like that, and learn Adobe Illustrator. If you have not seen Adobe Illustrator Creative Cloud Suite, you have full access to that. Download it, go to Academic Innovation, probably Academic Innovation. I have a link on the simple syllabus. You can go there. You can have an appointment. You can learn from them. They have videos. This is a good skill to have. Try to utilize it, and then start thinking about making the concept map, which will be due on November 28th. And I think we should go for like a social media kind of voting system. We can decide which platform or multiple platform and the actual way of doing it. But let's make it more fun, and so that like we make it more accessible for many people to, like if it's on social media, like many people can watch it. So you will submit a PDF of your concept map. We'll put it up to voting. The exact details we'll decide how to do that. So the voting period will be from November 28th to 3rd of December. On 5th of December, we will decide the winner. Everyone who submits the concept map, a decent one, like will get 5% of the total. And the winner, based on the voting system, the winner will get an additional 5% on the concept map. Okay? Class presentation will be on November 30th. All have to be present. So let's look into your calendars. Let me know whether you are available on that. If I do not hear from you in the next 1 week, I will assume that you will be present. Let me know if that doesn't work out, and we can play around the dates. I ask this is a hard date. We have to decide it starting off because everyone has to be present. You will get to know what the other teams are doing, ask questions and things like that. But also the first authors of these papers will be present to see how you did on their papers. So I need to get appointments. I need to tell them I need to give them enough time so that they are present, okay? You have to start forming groups. There are about 12 people here. I think 3 undergrads and 1 grad in one group would be a good combination. 1 grad student each group would be essential because that grad, so I would need, I think there are 1, 2, and 3 PhD grad students, and you need to submit a paper on that, a 2-page LPSC style paper. We can discuss more on that later, but each of this has to have like 1 graduate student in them, and the different topics would be environmental science and aqueous geochemistry topic, which is lead solubility in drinking water. So this paper, which uses concepts of environmental science and aqueous geochemistry to understand what's the composition, what's the concentration of lead in drinking water, how can you suppress it, and things like that. I've not read the paper, but I know the first author. She's extremely talented. She's at University of California, Berkeley. She's a scientist there currently. So this was published in 2021 on ACS Earth Environmental Science and Technology, good journal. The other one would be a combination of isotope geochemistry, planetary sciences, and atmospheric sciences, and deals with nitrogen isotopes in Titan's atmosphere. So that the lead author, Kelly, is a senior scientist in the Southwest Research Institute. She is deeply involved in the Europa Clipper mission. She is designing a mass spectrometer that will be on the Europa Clipper mission that is going to be sent out like really soon. So it would be good for you guys to meet someone not in academia but doing research in a company like Southwest Research Institute, very good institute for planetary research. And this one is based on concepts of planetary geochemistry and aqueous geochemistry. I am the lead author on this one, so I will So this would be my paper. So this was published this year in January, very fresh. A little controversial paper because this refutes the idea about oxygen on Mars. So good paper. So interesting, at least, if not good. Interesting, we are trying to understand like how oxygen was there, how people think there was oxygen in Mars's atmosphere, and how I think it's not. So it's like that. So form groups and choose papers out of this 3. Let me know. I'm not going to form it for you guys. And if like there is some problems in selecting, if multiple people wants to do one, then we'll do a lottery system. So, okay, cool. So last class we did phase. We talked about phase and phase transition and things like that. We also learned a little bit about evaporation, boiling, things like that. Were you guys able to go and clarify the concepts for yourself, or because I'm not going to do that again. It's there. Go there, read, listen to those 6 videos that are there on the general chemistry. A lot is there. So, did anyone find it okay? It was informative, useful use of your time. Okay, good. All right, today. What I thought we would finish with the piston cases that we were doing, in which a gas was inside a piston cylinder, and how the different cases, like when you increase the area, when you increase the density, how does the pressure change? Because we had a discussion about pressure, so I just thought I will finish that, and then we'll go to atomic structure. We'll think about really simple concepts like subatomic particles, electrons, protons, neutrons. What is atomic number, mass number, different kinds of isotopes. What are isotopes, isotones, isobars, isoelectronic species, things like that. And we'll touch upon a really simple concept, electronic configuration, in which we have this KLM, like the shell, kind of like the electronic configuration that you might have learned from in your high school. The 2n square rule, 2, 8, 18, those kinds of things. And then, this is what I would suggest you do at home, the electronic configuration with the SPDF, extremely important concept. This I wanted to do in class, but this is a part of the atoms and molecules playlist, which is chapter 6. I start here, and I think chapter 7 also discusses with some of the problems. Now this, if you do nothing, just to do this will change the game for you in chemistry. Electronic configuration, and we can discuss the problems based on the questions that you might have in class, right? Extremely important concept. I think one of the most fundamental tools that you will use to understand anything, any behavior of atoms in general through electronic configuration, through the SPDF. And I believed like you did not have so did you know about the different orbitals, like the s orbital or the p orbital, in which the s has a spherical shape, p has a dumbbell shaped, d has a double dumbbell shape, things like that. It's that. So using the concepts of orbitals and principal quantum numbers, things like that, it will be dealt here. Then we'll discuss about principal quantum numbers, and you can see in your problem set in here and the previous problem set, the practice problem set that I gave, there was a lot of electronic configuration questions there because it's so important. What I'll not do is get the Bohr's model of electronic configuration and electronic transitions now. So when you have the Bohr's model and there are energy that you can calculate for each orbital, and how electronic transitions of electrons from one orbital to another, I will not do that now. So all the electromagnetic thing, we'll do it later. So that is more like suitable for a period of class, I think it would be, when we do X-ray diffraction, diffractometer studies, that would be more relevant, because electronic configurations and how the different electrons, when they jump from one energy level to another, the release energy and how much energy is released, those kinds of things. Those are very important concepts, but for practical purposes, it's mostly theoretical, so that's why I'm not going into that. It's extremely important. There will be many questions that you might that might be there in the practice problem set, but it was since not very relevant and not very applicable, and that's why I'm like not doing that, although that's very fundamental geochemistry. Okay, so let's finish with these piston cases. So what we had in the last class was we had a system in which we had gas molecules which are moving, which are always moving in all directions inside, and this is not a good representation of gas because this is like too close together. Okay, but for our purposes, let's assume this is gas. We have a piston that can move in and out. So when you apply pressure, and what was pressure? Pressure times area was force, right? That's what we discussed in the last class. And why get a feel for why this piston, if you need to keep this piston at that level always, you need to apply a force in this direction. Do you remember why? What's the atomic idea behind it? Why would you need to apply a force on the piston downwards to keep the piston from moving up? Why was that? Brian, you were not in class. Can you take a guess? Sorry? What was the question? So this is a piston, okay? So it's like a gas container with a movable lid. So this can move up or down, right? Now if you have a gas in here, to keep this thing at this position locked, you need to apply a force from top.
When you study, it needs to be an equilibrium. So.
Yeah, so why do you need to, so if I leave it, if I remove my hand, this thing is going to go up, right? Why do you?
Gas wants to expand. It wants room, wants to expand.
And why? Gas wants to expand.
Are repulsive and they're pushing against each other.
Sorry?
The repulsive forces are pushing against each other and keeping each other away.
The repulsive forces, remember, so you used 2 or 3 terms here. So you used gases are expanding. Now I'll ask you why, or how can a gas expand? That is one. And the other is repulsion. Now, from the first class, we knew that gases will only repel, the 2 particles in a gas state will only repel. When do they repel? The atomic hypothesis says that the different particles will generally attract, but they repel only when
increase the temperature.
They
increase the temperature.
They do, right? But keep the temperature constant. But when, so yes, okay. So you gave an answer to this. It expands when you increase the temperature, right? But I drew this diagram in which things are getting closer energies, and how do you become more stable? By lowering your energy, right? So there is this point, if you get nothing from this class, just get this thing. The thing, if you want to become more stable, you need to release energy. That's it. That's the prime dictum of like chemistry. I do not know what you do in your day-to-day life if you think about these things or not.
Animal science.
Okay, so the animal which releases energy is more stable. Mm-hmm. The more energetic animals are more unstable.
Right.
Right. So When they are close, when they're coming closer, their energy is decreasing, they're becoming more stable. But there comes a point in which their energy shoots up and becomes really unstable. When two molecules become really close to each other and they want to push against each other, that's the time their energy will go up. But Hunter, you were right, like the temperature is one of the reasons that expands it. But what is the general reason that this thing is pushing this piston up?
Pressure.
It is pressure, but what is that pressure? Why is it doing it?
Because the gas molecules are constantly hitting.
Exactly. The gas molecules are constantly hitting a piston like this. So they're constantly in motion. If human beings had this, like if we develop like this heightened sense in which we can feel individual atoms banging on this, we would feel it, but we don't. So we get an average effect. We do not feel, so if I throw a big ball, you might feel it on the other side, like boom, there's something. But these things are also doing the same thing, but we don't feel it. These are so small and we are so big in scale. So we don't feel that. What we feel is an average effect that, okay, this thing is like getting pushed. And that is pressure, that average push that you are feeling because these molecules in small numbers are banging on that. This is immovable. So that's why you don't feel it. But this thing is movable, and that's why it's getting pushed. And to not get it, let it push, you need to stop it, right? And that is pressure. How can you increase the pressure? So Brian suggested expansion, and then Hunter said, increase the temperature, right? You increase the temperature, so your pressure increases. So now we also talked about the area. So if you increase the area, the force that you are applying should also increase, right? So if you have, like if this thing becomes something like this, increase the area, this force has to be more. You have to apply more force to keep this whole piston to move out, the same amount of gas. But now you're exposing that entire piston's area and more molecules can hit it. In here, maybe a little, maybe 5 were able to hit. In here, if you double it, 10 can do it, right? So increasing the area, you increase the area, the force that you have to apply increases, right? The second is the temperature. Increase the temperature, what happens to the molecules themselves? Take a guess. Just increase the temperature. What will happen?
They vibrate.
More,
Yeah.
right? So the vibrate. So you used the term vibrate. So what is vibration? It's a kind of motion, and motion brings in kinetic energy, right? So when they are moving faster, the temperature is increasing, and that, what will it do to the force applied? What you need to have more force to accommodate that, right? Any doubts? Any confusion? It's a simple concept, like essentially. So that when you increase the temperature, the force and the pressure increases. Third, increase the number of molecules. You have 10, make it 100. What is it going to do to the pressure? So you increase the density. What is happening? When you increase the density, what is going to happen to the pressure? It's going to go up, right? Any doubt? Is it clear? Okay. Now, when you push the cylinder in manually, now you are not just stopping it from getting pushed up, you're actually pushing it in. What do we call that phenomenon? When you're trying to push in, you're trying to what the gas? Compress the gas. So let's This is a good case. Listen to it carefully. When you compress the gas, what will happen to the temperature? This is a question. Think about it.
It'll increase?
Should increase.
Should increase. You have to give explanation.
Well, as the particles begin to bang into each other, they get more excited. And as their energy increases, so does the heat.
Good. That's exactly what is happening. So when you are getting that piston to get it in, so the gas molecules that are hitting it with more energy. Compared to something that is just sitting there, the gas molecules, when they hit a moving inward piston, their energy, when they bang back, when they rebound, it's more energetic. Does anyone have any problem visualizing this? Because I had.
I had a question about, because I'm going to like the Mariana Trench,
Okay.
where it's like really high pressure.
Cool. Yeah.
And I think, there's an abundance of area down there, you would imagine, but the pressure is so high. And so I'm kind of thinking about it there, where, you have more space for the atoms, but the pressure is kind of disproportionate to that.
That is a very different system than this. Right. That is a very different system. That's like
Shouldn't be kind of trying to...
So what is your question then? Like, are you trying to understand this using that analogy, or like, come up with the question?
Yeah, because your question was about...
You increase the external pressure,
Yeah.
and the temperature increases.
Yeah, but in the Mariana Trench, it's like really cold, right?
Yes, but the question is really different there and here. So the temperature. So I can take this entire thing and take it into a refrigerator. It becomes cold. But I am trying to understand what happens to the temperature of the system when you're compressing it. It's not the temperature in general. So even there, in any system, when you compress, it doesn't matter. I can take it in the refrigerator or outside. Whatever that temperature it is going to increase, right? So that's the idea. I'll just check if the camera is going. It has a 30-minute stop.